be giving a talk about a project that me and Eric, who's talking later today, started called Spire. The talk isn't really about Spire. It's supposed to be about kind of solving a nice little toy optimization problem that I thought was kind of fun. And then in doing so, kind of using Spire throughout and just seeing some of the little features it offers, maybe hopefully getting people interested in just seeing what's there. So anyways, the main thing is I work at Which Relevance. This is a company that does product recommendations for online retailers. So like, if you go to Target, you might get some lovely stuff there recommended to you. So we do that. And one of the things I thought was kind of interesting here is, some of our various personalizations depend on a set of weights. And sometimes these weights are just kind of chosen heuristically based on what people think will be good. And one of the questions, can we optimize these weights without actually depending on a human being? And what I thought was interesting is that, one of the real tools we have in terms of determining optimization is that we basically actually can sit there and we can split the traffic when somebody hits a site, and one person can get one set of weights, another person can get another set of weights. And we wait long enough, eventually we'll get some metrics out, like the revenue per session, or something else interesting like that. And why it's interesting is because it actually does take a certainly non-significant amount of time to actually calculate these metrics, and that can sometimes mean that our actual iteration sort of time to optimize things is quite slow. So anyways, this talk is basically going to go over gradient descent. So it's a very simple way to optimize things, and it's ideal for this talk because it fits in 30 minutes. So anyways, the goal is that basically you're at some point on a curve, and you want to get to the minimum of it. You don't know where the minimum is, but you just know you want to get there. So the idea is that you basically find the gradient at the point where you're at, and you travel in the opposite direction. And if you take a small enough step in that direction, you'll get a little bit closer towards the minimum, or at least the local minimum. So basically, you can see you take this little step, you repeat this, eventually you'll stop moving, you've reached the minimum. Pretty straightforward. So anyways, the requirements are pretty straightforward. We basically need an initial sort of place where we're starting. For us, it's our weights, our initial maybe heuristic weights we've set up. We need a step size, and you can get very fancy when choosing this. We're just going to keep it fixed for this talk. But the important thing is we need to be able to calculate the gradient. And if we have the gradient, we basically have this very simple iteration loop. You can see here. So we have our initial weight that we're starting with, and we're basically just subtracting from that weight, we're just moving in the opposite direction of the gradient. And we're just scaling that by some step size. And we get our new weight, and that's basically it. So obviously this is a talk on Scala, so I'll put this in a language you can understand, which is Scala. So you can see here, basically we have these nice little type aliases to help us out. Our V is the vector type, which is just an array of doubles, and our type A is just doubles. And basically what we've left the gradient implementation unspecified. You can just kind of ignore the I for now. We'll see why we're using it later. But really we just want to be able to give it some weight V, and then get out another weight V, which is the gradient. And we've just encoded that little iteration formula directly. And you'll see here, though, is a little bit of Spire coming into this. So we have this little operator, this star colon. So this is Spire's scalar multiply operator. So the gradient returns a vector, and we're just multiplying it by the scale of the vector to get a new value. We also have a subtraction here, and we're subtracting two vectors. So we're not subtracting two numbers, we're subtracting two vectors. So these are just nice little operators. We're operating on array. So the question is, why does it work? I'm not going to get into this too much, but basically, so double is a field, don't worry about the name. Array double is a vector space, and we can basically, that means that we can add and subtract the vectors, and we can multiply them by the scalar of the vector. So I'm just going to take a quick detour and go over the actual stuff that we'll be talking about this. You don't really need to know too much about this. Just kind of pay attention to the nice little operators we add and whatnot. But the main thing is, basically for a field just means that we have some type that's going to behave more or less like we think a number should from elementary school. So we can add them, we can subtract them, multiply them, we can even divide them. The division doesn't have to be exact. Like integer division does not behave like a school child would expect it to behave. Well, I guess maybe we can do but anyways, and the important thing is there's instances for all these things. Is anybody here not know what type class is? All right, fantastic. So anyways, yeah, all these things inspire type classes. So here's a quick little example we have. So we have the first import here, just basically provides all the little syntax we see. This is the only time we'll really see it here because I want to keep the slide short. But basically, you can see we have some little magic here. We have the implicit parameter for field for A, and once we have that, that means that we can sum them up and we can divide it by the size. But the important thing here is so the field A.0 is just shorthand for that. So I mean, I just want you to have to worry about that. Sorry. You can see we just sum them all up, we divide it, we get our mean. And then the important thing here is we can run it with floats, doubles, rationals. It doesn't really matter. So that's kind of the benefit of using Spire, is it provides an abstraction over number types. So what is a vector space? We've already seen the vector space in action. You know, we subtracted some vectors and we multiplied them. And that's really just what we want to do. It lets us work with a nice little type like array of doubles instead of having to code our own. We also need Approximate. All this really does for us today is it gives us the dot product. And all we're going to use that for is to kind of get some notion of the length of a vector. And then ordering. Order is just like Scala's ordering type class, except it's specialized, so it's a little faster for primitives. We have a nice little example here of sorting a bunch of numbers with an order. So we just have a little quick sort thing here. Oh, I have to put sort RS there, but it doesn't matter. And that's into the detour. Hopefully we can just get that. Anyway, so this example, we had our type aliases before with V and A. The question is, do we really actually care what V and A is? I mean, you know, here it's array and double, but you know, if they don't have to be array and double, if they just behave like we expect them to behave, then we can just get rid of them entirely. So we'll just put them in the type parameters there instead. And then instead, we'll just say that we require these things are, you know, V is a vector space and A is a field. And this should hopefully do it for us. So yeah, the next part is the optimization loop. So basically, you know, we don't want to actually call next weight ourselves repeatedly. We just want this thing to do it for us and eventually stop once we reach the minimum. So to do this, we will need the V to be an inner product space instead of vector space, because we will use the dot product. However, so you can see we have our little implementation here. It's pretty simple. A lot of things are hard coded because procrastinated. Anyways, yeah, so you can hear we give it basically the step of the learning rate. It's a fixed thing. And basically our loop is very straightforward. We have our WN, you know, from before, and we're just basically, we have our iteration number. We'll use that later because we need to actually see how long things take to run. And basically we just perform one step, and then all we do here is we then check if we converge. And we just do that by taking the delta of the two vectors. We use the dot product to get some notion of length out of this, and we just check to see if it's greater than, or if it's less than some value. If it's less than some value, we assume that it's close enough to the minimum, so we stop, or a local minimum at least. Yeah, and you can see at the bottom here, when we actually do first call, we just pass in the 0 vector. So we're always just starting from 0. We may not want to do that, but we're going to do it for this example. So anyways, to test it out, we'll solve the problem of linear least squares. So basically, we just have a bunch of points, and we want to fit a line to the points. And the goal is really just to minimize the sum of the squared distances from the points to the line. So we use a lovely function here. You know, it just uses the mx plus b sort of notation for a line. We're just subtracting our actual y position and squaring. We're summing them up over all the points. So can we use gradient descent to do this? Yeah, of course. Why not, right? The most important thing here is that we just need to be able to calculate the gradient. So in 2 dimensions, it's pretty straightforward. You know, so our function is basically, as we showed before, was just the sum of the squared distances. So if we just ignore the sum and we just deal with one point at a time, we basically just have this mx plus b minus y squared, and we just take the derivative of that. So we have these two partial derivatives here. It's pretty straightforward. And then, of course, the actual gradient, we just sum them all up over all the partial derivatives. Of course, that's not very interesting. We'll move to any dimensions because it's pretty straightforward to map that over to them. So basically, what you'll notice here is that we've switched over to using the dot product instead of just multiplication. But our actual, the derivatives are actually very similar. You know, basically we just have the same thing at the end. We don't actually use a coordinate, we just use 1. The important thing is the thing in blue here. Basically, we're taking the dot product of our coefficients, which are beta, and our weight. So the coefficients come from the point. We subtract the y value, and so we have a Scala there, we multiply it by 2, and then we just scale the vector by that, and we get a result out. Anyway, so in Spire, what we could do here is basically we extend our gradient descent thing, which means that we just have to implement gradient. And so to do that, you can see that, you know, for our betas and our ys, that just corresponds to our beta and our y there for each of the points. So we just zip them together, and we just get our little formula. That's the thing. Encoded, it looks very much like it does as a formula, so it's kind of nice. And then we basically just sum them up, and we divide them by the size. And we divide by the size just because it makes it easier to choose the step size. We don't have to worry about depending on how many points we have. Anyways, yeah, so testing it out. So now we just actually want to run this and see how it works on a set of points. So this isn't too important to notice, but I want to point out here is basically Spire has a random package which Eric created, which is really nice. And the most important thing here is this dist class, and basically what it means is that if you have a dist of arrays of A, it means you have like a distribution of arrays of type A. And we can sample from this distribution and get a bunch out. And so it's kind of like if you use Scala check, it's kind of like Scala check's gen, but it's more focused towards kind of like what you might want to do, I guess, in Spire. So anyways, basically, yeah, we just, our actual linear here will basically just generate a bunch of points along the line and just perturb them on the y, you know, by some Gaussian. So, or, you know, plus or minus. So we'll kind of get this nice sample which should fit it. And then we basically just use our least squares notation to optimize it. It goes to the gradient descent loop and hopefully stops. So basically I just ran it with some points. You can see here the line looks pretty good. Doesn't quite match what we originally gave it, but it looks like it's still a good fit. Anyway, so back to our original problem, which was optimizing weights in something like a personalization product. And can we use gradient descent? So the one requirement that we need is the gradient, which we easily got from the linearly squares, but it's not so easy when we're talking about something like revenue per session, because the function is basically people clicking on products and us actually having to wait for it. You know, we don't know what that is really. So that's a problem, but it's a problem we can solve. We can solve it by approximating the gradient. So you know, one way, if you have like a sample of points around that point, you can fit a polynomial, or we can just fit a hyperplane because we've already implemented that with the linearly squares. So that's nice. So yeah, let's just, sorry. So what we can just do is use exactly what we just made. We'll sample the points, we'll run it through our least squares gradient descent optimizer, and we'll get a bunch of coefficients out that'll give us an approximation to the gradient. Okay, so this is our version of the gradient descent that uses that does sampling to actually create the gradient. So right now you can kind of ignore the time span, but basically what it is given an iteration, it'll give you a range of time that we have to run that for, from like, you know, day n to day n plus whatever. And basically the most important thing for this is that we need to be able to sample. So sampling is kind of cool. So this is using Spire's random package again. You can see here that all these methods are from dist. So we have a way of, so like in this case our uniform is basically going to give us uniform distribution of A's that's distributed between negative D and positive D. And then we're just going to create an array of those. And the array is going to be the same length as our vector. And then the constant is just going to basically create a distribution that always returns the exact same value over and over and over again. And what's kind of cool here though is that the distribution will take on the same structure as the type as the distribution of. So because we have a distribution of arrays of A's, and the arrays of A's are a vector space, so is a distribution of arrays of A's. So we can just add them together. So we can take a constant, add some noise, and then sample that to get our sample. So the gradient, you can see here, we just basically do a sample, then we use our least squares implementation we just made, and we basically just take the values, average them over the span of time for each sample, and then optimize on that. For the actual gradient, we don't need the last intercept. It's completely irrelevant, so we just drop it. Yeah, so what's the time span thing? So this is the part I thought was kind of interesting, is just that, you know, like, people kind of, people shop differently on weekends than they do during the day, during the weekdays. And so because of that, the function is actually not the same depending on if you sample on a Monday or Tuesday or Saturday or Sunday. And so that kind of throws a wrench in the works, because if you assume something like there's a period of a week to this function, then in order to be accurate, we want to sample over a week. But a week is a long time to sample over for one iteration of something like gradient descent. You know, it's just not really a viable thing. So anyways, we basically make time an explicit parameter so that we can sort of control this and test it and see how it affects. Anyways, yeah, so yeah, the important thing here is that we basically need to evaluate f as some sort of weights. But the problem is that, you know, we need to wait an actual finite amount of time, like hours or days or weeks, to actually get a value out of this, like revenue per session for a set of weights. And so we want to be able to optimize x while still being accurate. You know, if we keep it too short, then it's going to vary a lot. If we actually do it over the full week, it'll be accurate, but it's full week. So let's check this out. So yeah, as I said, our main assumption is that we'll just assume that the period varies over a week. And so we kind of think of some strategies to deal with this. We'll fix our x to like just 1 day. We'll always sample for 1 day and then use that as our f. Or we can sample for 7 days. Another way is we can just ramp up from 1 day to 7 days over the course of time. So, you know, we kind of can iterate a little bit faster at the beginning, but get more accurate as we go. The last one's kind of similar, except we just skip 2 of 6 and we just jump immediately to 7 after some fixed period of time. So the first strategy is pretty straightforward. I'm not going to go over it, we basically just literally wait that many days, always. Strategy 2 is we ramp up. So here's a little bit more of Spire. So basically we are using Spire.math.min. Spire has a lot of functions inside of its Spire.math that kind of copy the Scala versions. The big difference is that they're specialized by and large, and they also include a lot of things for like big decimal and whatnot, which Scala's misses. Anyways, so yeah, this one will ramp up over a certain number. So we have a number of iterations, and we have a number of iterations, and we have some max. So, you know, we basically wait like 100 iterations, and we go up by a day. Wait another 100 iterations, go up by a day. Pretty straightforward. Strategy 3, we basically just wait like, you know, 200 days, and we jump up immediately to 7 or something like that. Days, starting from 1. Anyway, so yeah. So now we want to actually generate the data. So this isn't really that important. What I really just want to show you guys is Spire's Q sorted by and the Q search here. So Spire adds a bunch of methods onto things like arrays and sequences. In particular, it adds sorting. Eric implemented this and he's fantastic, and it's fast because it's Eric. Searching is like, you know, binary search. Everybody hates implementing binary search, so don't do it, just use Spires. And then we also have, you know, linear time selection, which is something that gets missed out a lot. I know C++ has very few other languages built into the standard library. Yeah, so anyways, then we basically just implement this little function that'll be periodic over the week. The important thing is here, you know, we kind of have our weekends where our values are a little bit higher and they're shifted, and then we have our weekdays that are a little bit different. And so the minimum over the week is 2.3, so that's really where we're trying to hit. So this is basically 2 dimensions in here. We're just focusing on, or sorry, 1 dimension. We're just focusing on getting the proper x value. And that should be 2.3 the minimum. So our goal is to get as close to that as possible. So what we prefer is for our stuff to converge as fast as possible. But we also want it to be accurate, because, you know, it doesn't matter if it converges in 3 days if it's completely inaccurate. So these things kind of compete with each other, which is not fantastic. Anyway, so I basically generated a bunch of data and ran it over like, you know, 60 times. And to see how things pan out, and the results are that there's no free lunch. The things that do really well in terms of the error, like the fixed, if you just do 7 days fixed, the error is very low, but it takes forever. You know, like that's literally like a decade of time almost, waiting for this thing to converge, which would be terrible, right? 1 day converges very fast, but it has a terrible error. I mean, that's way off the mark. And sort of even the ramp up I thought was going to be good. It was kind of terrible. The jump ups were kind of, you know, as you'd expect. As the jump up moves further and further, you get more errors, but it converges faster. So I mean, what do you do, right? So I mean, like, yeah. So to me, like, this is kind of the best solution because it's kind of a nice compromise between the two. That's still a really long time. I don't think that's really a viable solution in the long run. Yeah. That's it.
I'm really curious if, so does this
So I mean, we're working on arrays and vectors right now. We don't have a ton of support. So we have a guy working on a whole bunch of linear algebra support, so adding basically matrices and operations on them, but it's not in Spire. Yes?
Can you thought like doing some of the math lazily so that like you confuse things, you know, like AX plus B. I want to do that in one loop if I actually care about performance, right? I don't want to do two. Is there anything exploiting some of that to do?
There is. I mean, like, so yeah, we definitely don't quite do that yet. That is one thing that I've had my kind of heart set on for a while. And especially trying to explore, like, you know, doing that in some interesting ways, especially use like macros and things. I think me and Eric talked about kind of having, like, you write an expression, you basically wrap it in something, say .fuse. And what it would do is it would look at that and create a little AST and then pass it into, like, some other little bit that can actually generate, like, a faster version of it. But no, we don't have anything that built in. I mean, as you know, the real thing is kind of like an AST. Anything else?
So there are several linear algebra libraries for Scala. I think there is Breeze, and there is a Settle, which was announced at Scala Day. So I just wonder, did you compare Spire to those? What are the differences? What are the advantages?
Right. So Saddle basically provides actual concrete instances of these, like, you know, like a vector of, like, that you can actually use, right? So Spire's main goal is really to provide the abstractions. So, I mean, Spire would kind of fit into Saddle in the way that you'd write a vector space that uses Saddle's number types. And then the idea would be that you don't have to tie yourself down to a particular type. You can kind of abstract over it. Yep.
Do you use any of these techniques, like, at work, like in terms of various optimization problems you're doing for rich relevance or things like that?
Yeah, we use a bunch. I mean, it's I don't know if I can get how specific I can get, but I mean, yeah, I haven't worked there for too long, but yeah, I mean, like, we were kind of exploring these things, which is where this talk came from. And I was using, yeah, it's kind of using Spire to do a lot of the little, like, adding, like, because I just need some operators and searching and that kind of stuff, which is why I gave this talk. Cool.
All right, thank you.